Welcome to our 6th lecture on photovoltaic energy systems. Today we will discuss the second part of photovoltaic systems, the mounting, so-called BOS, it means balance of systems costs, the on and off grid systems, and total costs. So if you see the total cost of a PV system, see that a relatively small part is for the silicon wafer, and also 20% is for the solar cell technology, and 25% is for the setup of the module, as you saw, just the stringing, the setup of the matrix and the lamination and the integration of the frame and the terminal boxes. But a very large part is the installation, the support structure, inverters, land and ground preparation, which amount to about 35%. Here you see some examples of distributions. This is now for roof-mounted systems in Germany for 10 to 100 kilowatt systems. And you see the development of the distribution of the costs. So formerly in 2006-2007, you saw that as 71, respectively 74% had been for the modules, and only 26 or 29% had been for the BOS costs, including the inverters. While the costs of the modules went down significantly, this changed totally now. If you see just the end of 2018, it doesn't change so much for 2019. You see now that nowadays about 45% are for the modules, and the majority, the larger part, is for the BOS costs. So it really is important to take a look at that, because very often I see people just they think about where I get the cheapest module from and should we set up a factory, but you see here that the most of the money allocation is at this BOS costs. So we take a closer look at that today. So for example, mounting structures, we have to think about technical considerations. What have to be taken into account? That's the material. Is it either steel, aluminium, or sometimes wood is the best? For example, if you go close to coastal areas, there the air is rather salty, which causes a lot of corrosion at the metallic structure. And if there's a lot of wood available, then wood is not a bad option. Maintenance issues is also an important thing, whether you have people which can do the maintenance or whether the system is rather far away from the next town or so. So it's a really big effort to carry that out and so on. This has to be included in the total price. Yes, corrosion resistant in a moist environment, so either aluminium or galvanized steel. As mentioned already, in a salty environment, wood could be the best option. Powder coated would be the best option, but at least a hot dip galvanized steel is required in order to reduce the maintenance requirements and to increase lifetime. A variable height and a mounting angle, that's sometimes important if you have an uneven ground and you still want to fix the modules in a straight way, then you should really be able to adapt it a little bit, also with the mounting angle. Accuracy and tolerances, even if you don't have an uneven ground, if the manufacturer of the mounting substructure has a high tolerances in its fabrication, you end up in difficulties in mounting the equipment, and even can even lead to damage if the people try to press modules into a structure which doesn't fit. The ease of installation and the effort of disassembling is also, as I mentioned already, is important to include in the cost. Lightning carrying cables, sufficient grounding. It's important if you live, especially if you live in an area that suffers from a lot of lightning and so on. But anyway, it's always a safety measure to think about good lighting conditioning. Integration of the cable layout. So you want to make sure that the cables are protected against UV radiation, but also against wind, against attacking by mice or other animals. In some countries, it's even required by law to put the cables in a housing. For example, in the United States, you always have to put cables in a metallic tube because many houses there are made out of wood and there's a danger of fire, and therefore all current carrying cables have to be encapsulated in a metallic tube. Wind load. So you want to make sure that during the lifetime, which was formerly calculated to 20 years, but nowadays it goes to 25, 30 or even sometimes 40 years, you have to make sure that there's a very little probability that there's a very strong wind during that time, and you do the layout for that. There's a compatibility with actual PV modules. You have to have the fixing mechanisms. You have to just check the instruction of the modules where to put the fixing mechanisms and the screws and so on, and it has to be in correspondence with the substructure, the mounting structure. Layout of the construction, fix of module arrangement, wiring. We did it last lecture. And yes, as I mentioned already, the mounting structure should be able to neutralize a slightly unevenness of the ground. Here you see the interconnections of components of a mounting structure. For example, number one, this is just fixation to the external edge of the module. So this is a traditional one. If you have many modules together, you can use fixation between two modules. So you just have one screw to fix up two modules left and right here. And you have to fix also the module and transversal beam. It's shown at number 3, and fixation to the ground and foundation pile. So you see here it's adaptable. We see some more pictures on that. Here you see just depends on how good the fixation of the foundation is. Sometimes there are some tolerances and you should be able to adapt to that, otherwise you end up with strong mechanical stress in the module structure if you force the modules in and so on, and this could lead to micro cracks in the solar cells and to a reduced lifetime of your power plant. Here you see some examples. This is a very old style. Here in 1994 you made a concrete structure which takes a really long time and it's rather expensive. Or here even on the right side is in the Swiss Alps, a very massive construction which lifts the BOS costs considerably. A bit easier are so-called gabions. These are containers which are filled with rock, broken concrete or other material, and they serve the same as concrete blocks. Okay, they don't fix as much, but from the weight and so on, they do serve the same, and they are much faster to install. You can also do prefabricated concrete modules to transport the whole blocks. You don't have to mix up the concrete mix the concrete on site and wait for several days until the concrete is hardened and so on. And this is already carried out, and so you can set up the power plant much quicker. You also can hammer the piles in without any foundation. This depends very much on the ground, so you have to do an analysis of the ground before, whether it's feasible. Sometimes if it's sand, you have to use very long piles. If you have other kinds of soil, then it's quite good feasible, because you don't need a very long pile to put in and so on. So you have to do some prerequisite research on that. Here in the middle you see just an adaptable joint here that allows just to tilt it a little bit and also to turn a little bit in both directions. Here you see so-called earth screws, which make it even faster, so it's not hammered, it's screwed into the ground like a screw on the wall and so on. We'll see a short movie on that, how they do that. They can, this is by the company Krinner, which was a pioneer in that area, and they show us a movie about how they set up a very big power plant with 300 megawatt in a very short time.
Just half an hour by car from Bordeaux is one of the largest photovoltaic building sites in the world. The modern high-tech solar park extends over an area of 2.6 million square meters, the equivalent of 363 football pitches. Thanks to the maximum output of 300 megawatt peak, approximately 111,000 households can be effortlessly supplied with electricity. As a result, approximately 230,000 tons of CO2 are saved each year in comparison with a coal-fired power station. For this mammoth project, the Lower Bavarian family-run company Krinner took over the planning and realization of the foundations and installation. The specialist for ground screws will complete the solar park in just 8 months of construction. The precise project preparation is the cornerstone for the rapid construction period. With help from special machinery developed by Krinner, time-consuming and cost-intensive risks can be calculated in advance. In the first step, the soil conditions are inspected to guarantee long-lasting stability and fastening of the foundations. In the second step, a GPS-controlled measuring robot creates a detailed site plan on which the markings for the ground screws are placed with millimeter precision. This allows precise and rapid positioning of the foundations and is the basis for the absolute adherence to delivery dates. The collected data is inspected and fully documented at the Krinner headquarters. The data is then transmitted directly to the on-site construction machinery via the Krinner cloud. This means the foundation work can begin without delay and with the utmost precision. The ground screws are screwed into the soil with millimeter precision. The fully automated process and the special ground screw drivers developed by Krinner make it possible to position the ground screws rapidly. The material-optimized patented design of the support frames adapts perfectly to the local conditions. As a result, Krinner can guarantee a high level of stability, low costs, and rapid installation time. Finally, the photovoltaic panels are quickly and easily assembled with a plug-in system developed especially for this purpose. Thanks to cutting-edge technology and efficient working steps, more than 4 megawatt peak per installation team can be assembled each day. In addition, the support frames are completely maintenance-free after assembly, which means no subsequent costs. To us, top-rate performance does not just mean extraordinary quality and reliability. It also means extensive checks. For this reason, we check our products exhaustively before approval, providing you with the security you need. Especially in terms of the project costs, our customers benefit from rapid commissioning, freedom from maintenance, and rapid amortization. 200,000 ground screws, 326 kilometers of support frames, almost 1 million photovoltaic panels. With a solar park in Cestas, the inventor of the ground screws created one of the largest solar parks in the world in an incredibly quick construction period. Thanks to Krinner, quality made in Germany.
This was a nice example, especially you saw that the east-west orientation of the module that helps also to reduce the midday maximum of PV modules and helps to put the modules more in a to produce more even or more balance during the day, so more power in the morning and in the evening, but we come to this a bit later. Now you see here more conventional structures on flat roofs here. You see that they have here some wind protection, so that helps that the winds can put a high pressure on the module and lift it up very easily. So this is purely aerodynamic. This is purely aerodynamic reasons why these are installed. Also, this is also a bit former to put a ballast on the roof and integrate the modules on that. Very simple installation. This is for conventional roofs. There are different types of Z profiles profiles which fix the module. So you have to make sure that the roof tile still protects the roof. So the roof tile goes over the profile here, and then this part looks out, and then you put a beam there to install the modules later. This hooks or profiles here that you have here. Here you see also there are special tiles which allow to let the cables pass into the roof. Here are clamps which allow to install frameless modules, which has been especially applied in the thin film area nowadays, not so much often used, while the module is quite sensible, and you have to use a quite thick glass in order to make the module withstand against the wind load. So nowadays modules have the classic format that they have just aluminum frame it, and they have a relatively simple fixation. By the clamp here you see a cross section of such a mounting clamp here. So you have here the modules here, they are clamped, and here fixed, two modules fixed with one single screws in order to protect the module. There's some kind of sealing here made of rubber in order to also allow the thermal expansion of the module. Here are some examples of those. Here are some examples on the back. You see very famous tracking systems in Freiburg, which is a house specially designed to go along with the sun. So you can, winter you can direct your living room directly to the sun. In summer, if the sun is shining very hard, you can do the opposite and turn it away. And totally independent from that, you have your solar generator, which is always looking in direction of the sun. Even in winter, at a very low elevation angle of the sun, as shown here, you can also put them almost perpendicular to the ground, very high tilt angle to accept all incoming, get most of the irradiance in winter periods. Here's also another tracking system. This is now photographed in a horizontal positions. This was a safety measure because I came there when there was a large thunderstorm the night before, and in order to minimize the attack angle, they put all the modules in a horizontal mode. Usually you don't do that in Germany because usually the sun never is hitting perpendicular on the modules. And or maybe if there's just diffuse irradiance, then this position is also optimal. If you don't have any direct irradiance, then also horizontal position is optimal. We will see now some details on that a moving system about solar mover. So on the left side you see the azimuthal tracking, and on the right side you see the tilt and the elevation angle tracking for these modules. And it goes along with the chapter irradiance, so I just do the azimuthal adaptation of the sun, and also the tilt and elevation angle of the sun. This was quite popular in the year 2008, 2009, because during that period modules had been quite expensive, and by this measure you gained about 30 to 40% more energy yield. Nowadays it's a bit less popular because the costs of the module sunk considerably, but the cost of the tracking system more or less remains the same, and therefore most installers prefer to install more modules, 30-40% more modules, for a lower price than the cost of such a tracking system. There's some development going on now to make a low-cost tracking system, mostly only single-axis tracking systems, but we have to see how long they last, whether they really last for 25 years or 30 years. If you talk about costs, the cost of a photovoltaic power plant depend on the PV module costs. This is also important to see the interest rate and the payment conditions, warranties and so on. Efficiency, lifetime, so there's some degradation. This was an issue some years before when a lot of thin film modules have been applied, that some of them suffered from some considerable degradation. Nowadays, rule over the thumb is you have about a degradation of 0.5% per year. So after 20 years, about a bit more than 10% of degradation. Motor properties, we talked a lot about the electrical properties, but also the mechanical properties, how much wind they can withstand, thermal properties, just the electrical impact on that we have a lower voltage, but also we need to know whether how big the thermal expansion is and how much does it fit to the substructure. The local condition, the area orientation, so if you go to more southerly locations, you need lower tilt angles. Then very local is a local shading there. Are there trees? Even in the future, if you see 20 years in the future, trees can grow. So you have to take a look at what happens in 10 years or so. The trees get bigger and whether they cause shading then. That's even included in modern simulation programs. You can give them the type of tree and it already calculates the growth of the trees in the future and the possible shading due to that. Sun elevation in winter, that's a big issue in Germany because, for example, in Berlin we have only an elevation angle of 14 degrees above the horizon, and so the shadows are very long and have a big impact on that. And this is also related to the next part, the distance of the road. So if you want to make really shadow free and want to really make sure that it doesn't happen in winter, you have to keep a quite large distance between the modules. The snow and the wind loads. You can even buy modules which are able to support higher snow loads if you install in alpine areas. So on. This is come to this later when we come to the test conditions. So you have modules which support higher loads. Soiling, if you, for example, install a PV power plant in the desert, there's some soiling by dust or by sand, and especially if you go to southerly locations, the module elevation angle is much flatter, so the soiling is more probable to stay on the module rather than to be washed away by wind or by water or infrequent rain and so on. Also birds can cause soiling. The bird shit there, and even some people may throw debris on the modules and so on. This is all has to be considered or find measures to get it away. Grid connection, that's an important issue if you want to sell your electricity. So most important is a PPA, your power purchase agreement, whether you have a premium tariff or make an individual contract. Then who has to pay for the interconnection? Mostly the investor of the power plant. So you have to consider the distance to the next grid injection point. The voltage, is it low voltage or is it mid voltage? Who has to pay for the transformer? And the maximum power. Photovoltaic change a lot, so at nighttime you don't have any power, but at midday you have the maximum power. and this has to be considered in the layout of the grid connection. Also, you have to consider the ground structure. Is it even or not even? Then this depends on the purchase of your substructure. Also, theft in some countries is a big issue, so you have to make a fence around it and have some security personnel to avoid theft of PV modules. Balance of system costs. So we have two definitions. So this is usually say it same as for modules in euro per watt peak, and the defense by the module design forward. So we have the substructure and foundation, the inverter and its monitoring, the wiring, connection, installation requirements, and the diameter, and the so-called EPC, engineering, procurement, and construction. This is usually done by a single company called EPC. So they do all the engineering, they purchasing the parts, and they also set up the whole power plant. Margin and profit is also an issue, especially if you come to a new market and people are afraid that they will lose money, and so they put a high margin on it. Usually if the market is more mature, there are more competitors, and the margin availability is less, and so are the profits, but in general the total cost of the module, the PV power plant, goes down. And yes, the risks, some mentions of pre-financing, exchange rates. If you have to import stuff, you have to consider especially customs. Sometimes this takes really a lot of time to import PV equipment, and other delays. So there could be the monsoon areas and you couldn't deliver the parts, or there's a strike and so on, or theft of some parts. It doesn't have even to be the modules. Sometimes just the tools are stolen, but you can't install them, and cost of insurances, and the commissioning to your to the buyer of the PV power plant, or to the utility which is purchasing the electricity. They have some certain requirement. You have to make an appointment. Sometimes this takes a long time. Sometimes they complain about something, so you have to some redesign and then do another commissioning and so on. This has to be also included in the BOS costs. As I mentioned before, there are two types of BOS costs. These are the mechanical BOS costs and the electrical BOS costs. The mechanical BOS costs are the substructure, foundation, module mounting parts, the screws, bolts, piles, or hooks, and the labor work to do that assembly. As you saw, the Krinner, this could be done quite efficiently. In the movie they said they are able with one team to install 4 megawatt of PV modules in a single day. So that is really, really efficient. In other regions and so on, this takes longer and it takes more manpower, and this has to be considered for the local conditions here. The electrical BOS costs, so these are all the electrical components to connect and combine the PV modules, the strings, the DC connection box, as you already saw, the wiring, as we already talked about in the last exercise, the inverter connections, lightning protection, the monitoring system, labor costs for sampling and installation, and so on. Here are some examples. Fortunately, this is a bit older publication, but was even looking up yesterday. I didn't find anything new, but so this is from 2012. So in general, that's still valid today, but the cost distribution may look a little bit different nowadays. So here you have GMS, that means ground mounted systems, and you see here the impact of the solar cell efficiency. So you have crystalline cells, they are the most efficient, but the most costly. You see here at case A, so the cost share of the modules take really a high part in that. If you go to the other side, to the right part, you can TF means thin film modules. So usually you have cheaper modules with a lower efficiency, so you need more area to cover, you need to buy more piles, more foundations, more beams, more screws and so on, and therefore the BOS part is higher and so on. So it's always a balance whether what to choose. Depends also, for example, on land costs. If you're on a desert, land is usually cheap. If you install PV modules in the middle of the city, land is really an important issue. So you opt for the most expensive but most efficient modules, which require less land. While you do the opposite if you go to a desert area, for example. Here you see the share of the different costs of a ground-mounted system. So you see here the cost of the substructure, then you see the wiring, the inverter, the wiring and the connection. Here you see the margin here. These are the mechanical costs. This is the mechanical installation and so on. So you see the cost distribution. These are shown different cases here, and here it depends on what technology you have, whether you have frameless modules or modules with frames, how many screws you need, and what's the installation technology. As you saw at the Krinner movie, they didn't even screw the modules on the beams. They just flipped them in, and that saves a lot of money in the mechanical installation. Here you see the comparison between ground-mounted systems and roof-mounted system. Here on the right side we have a flat roof, so you need to spend a little bit more money on the substructure, while if you have a pitched roof, here the substructure is limited to some hooks or some profiles there, and then the beams, and therefore it's drastically reduced, while the installation costs are really much higher because you have to put the people there, and they cannot act as quickly as on the ground because it might be dangerous and so on, and so the cost distribution is a little bit different. So see here. Also an important issue is energy payback time. So for not only the modules but the whole system, how long has the system to work to get the energy back that it has been needed to set up and to produce? And this is shown here. This is made for Germany now with a moderate irradiance level of about 1,000 kilowatt hours per square meter per year. And you see here the energy payback time in years. And here you see monocrystalline. You saw with, for example, the Tucholsky process, the silicon is rather energy intensive. So the silicon feedstock just alone almost takes a year to get the energy back, which you needed to produce the energy feedstock. You saw also the movie there from Wacker, which have been showing about the production here, the ingot and the crystal and the wafer. So you need 2.2 years about to recover that energy you spent there for production. For the cell processing, it's not a lot here. There's not many materials needed, and so just processing energy. And the frame also not so much. And the laminate here is considerably higher, and the mounting and the wiring and so on, and the inverter costs. These are all the same. The inverter expenditure is about almost the same. If you go to multicrystalline, you spend much less energy on the silicon feedstock and the ingot and crystal and wafer and so on. So you have less than half of the energy spent in total. You have just to wait 2 years until you get all the energy back you needed for production. So if you have a lifetime of 25 years, so for the next 23 years energy is for free. And if you go to thin film modules, here you see there's almost no. I think for silicon it's really little because it's only very thin. Just silicon is really sprayed on there, so you hardly see it on that graph. But you spend much more on the laminate and the frame and so on. And don't forget, you have to spend more BOS costs because amorphous silicon best efficiency is in the vicinity of 10%. So you have to have about double the area and double the ground area and double the piles and double the screws than you need as if you have installed it via monocrystalline modules. Here, microcrystalline modules look a bit better because the efficiency is considerably higher. Also, cadmium telluride, the latest records have been there in the vicinity of 18% of conversion efficiency. So here, of about 1.2 years, all the energy is being recovered. The main problem here is the occurrence of cadmium, which is not very healthy, and you have to make sure that after a lifetime you have to collect that cadmium and don't leave it in the environment. Here is CIGS, similar to the microcrystalline silicon from the energy payback time point of view. Here you see the scale of the efficiencies. You see it, as I mentioned here, amorphous silicon is at the best is 10%, most of them at only 7%, but it's really out of the market already because you see here the material itself is very cheap, but the following costs are really expensive, and so it's not much used anymore. Microcrystalline silicon is still used there, and also you see at 120 megawatt use cadmium telluride a lot, about 1 gigawatt here during that publication in 2013. And here CIGS considerably less, but also similar efficiency. But you see here the energy payback time is a bit higher. That also means you spend more money on different parts here. For example, here frames and so on. If you go to another location, that looks different. For example, if you now go to Spain, for example, you have here in the south of Spain, you have an irradiance of 1,925 kilowatt hours per square meter per year. And this is for the inclined module here. If you have a direct normal irradiation, so it's a bit less here. So you have here 1,794 kilowatt hours per square meter per year. No, this is not for Spain, sorry, this was Sicily, Italy. But irradiance conditions are the same. So here I think we got similar values for Seville when we saw this. And here Fraunhofer made that for Italy. You see here, there the maximum is already 2 years, but you stay below that even for the most energy intense way of producing here with the single crystalline silicon. Here, if you come to multicrystalline silicon, you are just a little bit above 1 year of energy payback time, and if you go to the thin film technology, besides amorphous silicon, you stay below 1 year on energy payback time. So this is a CPV, means concentrated photovoltaics. So if you use a mirror and so on, this is not so much often used anymore because you have to have a lot of direct irradiance share in order to make this profitable, which is usually not the case in Germany because most of the irradiance is indirect or diffuse irradiance, and there the concentration is useless. And also even in sunny locations, you have to have a tracking system to keep the mirrors tracking the sun, and also keep the mirrors clean, and these costs are really high, and nowadays they don't play a big role, even if the conversion efficiency and the energy yield is quite impressive. A very important issue are the carbon dioxide emissions. This is a quite a new publication which has been published last year on the European Energy Congress in Marseille. The investigation has been carried out in 2017, so 3 years old. Okay, it's not very new, but okay. You see here not only the carbon dioxide emissions, but all greenhouse gases. Therefore, it's called CO2 EQ. It's mean equivalent. So that's all which is liberated during production, CO2, but also methane and other gases which cause a greenhouse effect. You see the worst case is here some old style monocrystalline with a quite poor efficiency of 16.5%. So this was about 10 years ago. So this is not new photovoltaic, it's old photovoltaic. If you go to latest photovoltaic, with you just have a very high efficiency. This means also building integrated photovoltaics, so you don't have to spend a lot in substructure because you can attach to the facade or to the roof. And there you see a significant difference in the CO2 emissions. So it's not only the technology itself, it's also the way of mounting and so on. Here you see it, the wafer also quite important because wafers got thinner, plus the efficiency got higher, and here you see a drastically reduced energy requirement and accordingly CO2 emissions for the wafers. And also the mounting system got less and so on. Inverter stays the same for all technology. If you go to polycrystalline, this old-fashioned 16% has been also more than a decade ago, and nowadays 20% is easily reachable. And you see here we're in the vicinity of about 50 grams of carbon dioxide greenhouse gas equivalent for that technology. If you compare it, for example, to coal, the carbon dioxide alone for coal is about 1,000 grams per kilowatt hour of electricity, not counting still for the other gases, so it's more. And if you go to lignite, you already have 1,150 grams per kilowatt hour of generated electricity of only carbon dioxide emissions. Another issue what should be mentioned is also where you produce your module. If you have a production in China, for example, and you install in Marseille with quite high irradiance, then you have about, how much is it, 70 grams of carbon dioxide greenhouse gas equivalent per kilowatt hour of generated electricity. But if you go, for example, here the green part is Europe. If you go to Europe, it's just a little bit above 40 or 42 grams of carbon dioxide equivalent per kilowatt hour produced. So if the carbon tax comes into place, this would be a significant advantage for the European photovoltaic industry, which almost doesn't exist anymore due to the cheap prices of the Chinese production. But if you consider the future carbon taxes, which are already in place in Sweden or so on, in the vicinity of Sweden, I think it's more than 100 euro per ton of carbon dioxide. In Germany starts at 25 euro per ton of carbon dioxide, or Switzerland it's already at 80 euros per ton of carbon dioxide. This can be play an important role if it's considered also the production of products and their carbon dioxide burden. So mentioned already, depends on the location. Yes, it is for Marseille, quite a high irradiance, similar to the Sicily example in what has been shown in the example before. Here Beijing, yes, a bit more than Germany, but much less than in Italy or southern France. You see here also, you see this huge difference here. So we have about 85, 90 grams of carbon dioxide equivalent per kilowatt hour, while in Germany we only have about 50, 55 grams of carbon dioxide per kilowatt hour of greenhouse gas emissions. Los Angeles has the highest, and you see also here in Europe, if you have a European production, including transport and so on, we are below 40 grams of greenhouse gas emissions per kilowatt hour of generated electricity. So let's go to the system configurations. We go with the history. So the first systems have been off-grid systems. So started in space there because for satellite technology, photovoltaic, even in the 50s and 60s when photovoltaic solar cells have been extremely expensive. Photovoltaic was the cheapest option to do a power supply for space technologies, and so it's been constantly applied since the 50s or 60s. There's been some experiments with nuclear reactor in space, but they were abundant, and so it's a solar energy source of space technology is photovoltaics. Even during that time, this is from the Times magazine in 1958, people were expecting that prices will go down of photovoltaics in the future. It will serve as home supply. And what's really happened today, we can come later. When photovoltaic doing that, this is a picture from the 80s. So it was profitable already in very remote locations where you have to compete with diesel generators, and especially the transport of diesel. Even if a diesel generator was affordable, the cost for transportation has been quite considerable, and therefore photovoltaic, even with the formerly high prices of the solar cells, was competitive against those options. So the far away from the grid, the more competitive photovoltaic has been. This is an example from 1987. This is in Germany. Not everything is connected to the grid. This is a hut in the farming hut in the Black Forest. They formerly had a diesel generating unit, and then the Fraunhofer Institute, they said we can do something with photovoltaics. And so the owner had three options: either to purchase electric grid connections, 5 kilometers, which was 500,000 German marks, which is nowadays 250,000 euros. And this was a lot of money during that time. And so Fraunhofer suggested, don't buy a new diesel generator, it will break anyway. We suggest to make a building integrated photovoltaics, which was really, really seldom at that time. So they installed a 17 kilowatt PV generator, and the farm really got famous. So it was in many books about the Black Forest and so on. And even tourists were arriving. So the farmer's wife decided to open up a coffee because to host all the tourists which came there to take a look at that power plant then. It was still a diesel there, but a very small diesel to do the backup during winter time and during winter. There was a battery there, but it wasn't sufficient to supply the power during the whole winter. But anyway, the most of the energy has been consumed in summer because it was occupied in the summer mostly, and also the cows are only up in summer, and in winter they went down to the village, and they kept there in houses where you get grid connections. This is a schematic of such an off-grid system, often also referred to as solar home system, SHS. So you got your PV generator, then you got a diode which serves as a valve, so only let electricity flow out of the module, not in order to avoid in nighttime that the PV generator can consume energy. Then you had the charge controller. This is a very simple charge controller. Just show how it works here. It checks the voltage of the battery. Here's an example of a 12 volt battery, and if the voltage is below 11.5 volts of that battery, multiplied by a factor which is due to the battery temperature, which is measured here, and if it's below that value, then the load is switched off in order to protect the battery, because if you keep, usually during that time, these have been lead acid batteries, and if you keep them at a low charge for a long time, lifetime is extremely limited of those, and so you should avoid deep discharge at all time, and therefore the load was skipped. There were also different kinds of charge controllers with different priorities, so you first skip the non-important load, and only in a real emergency you skip the important load, and so when you got charge controllers with 2 priority loads and so on. And the other thing, usually you have connect to this, so it's always charging only when the battery voltage of this 12 volt batteries goes above 14.5 volts multiplied by that factor due to the battery temperature. Then you switch off in order to avoid overcharge of the battery and the occurrence of electrolysis or extreme electrolysis, which will take away the water content of the battery and will transform the distilled water into hydrogen and oxygen, and you have to refill it and so on. So this was also switch off criteria here to limit the voltage here of that 12 volt battery. And it was a load, could be even an inverter there, or just a ordinary 12 volt load, whether a TV set or lamps and so on, whatever you need. Yes, this is the same here. I guess you can also switch off the generator, not switch off the load of the battery, so there's different schemes what has been applied there. This is just a quick calculation. For example, you've got a daily consumption of 400 watt hour per day. So this is just the load and times of use. For example, if you got a light bulb with 10 watts and you use it 5 hours, you have 50 watt hours. And for 400 watt hours, so here this was the sunny location, you need about a panel size of 125 watt peak. We calculate this in our exercise more in detail, and usually if you have lead acid battery, you avoid deep discharge and a good value to keep a long lifetime, and still adequate installation cost is about 50%, so you only use half of the battery's capacity. And also you should consider what's the probability that there's a sequence of bad days or days almost without any irradiance. Usually in sunny locations or tropical locations, you can put that number 2 days of autonomy to 2 days of autonomy. In Germany, bad weather periods can last longer, so you usually take as a rule of thumb about 5 days for that. And for this sunny location, this tropical location, you arrive at a battery capacity of 135 ampere hours at 12 volts. If you multiply that, you have the values in watt hours. This is also now with an inverter here, so the same configuration, but here you have inverters. You can put conventional AC loads here, but you have to consider you have to buy the inverter, plus you have some losses here in the inverter, and this is considered here. So you buy a bigger panel in order to compensate the losses by the inverter, and also you have to consider a little bit higher battery capacity. These are some examples here for these charge controllers here by the German company Stecker here. Very nicely made with an indicator. This is SOC, means state of charge of your battery, and you can show different the amount of consumption and so on, and even is able to switch on and off your load and so on. And this is another control. So there are a lot of different types of controllers which have different indications and so on, and also different kinds of charging strategies, whether they charge fully from the beginning and then reduce charging. This depends also on the type of batteries you have, and we will come to that if we come to the storage. We will discuss about this in details. These are the inverter for off-grid system, here by the company SMA, here by a Swiss company called Studer. They have to have their own oscillator because they don't have grids, so they have to create their own sinusoid. And these are separate from the grid inverters because they are not able to synchronize to the grid because they create their own electrical supply and their own 50 Hertz supply or 60 Hertz, depending whether you are. So this is the layout of a small PV system with an inverter. So this is a formula to that. That's first you start not with the battery or the PV generator, you start with the determination of the load. So as I already mentioned, you have the power of the load. For example, your light bulb is 10 watts and the duration of use, for example, 5 hours. So 5 hours times the power of the 10 watts. And then the efficiency of the inverter, maybe 90%, so divided by 0.9. And that is one load then. But usually you have several loads. For example, here it's calculated for n loads. So you start with the I is 1, this is the first load. So it's the power, and then you have the duration of use. Usually you take the end of time use, for example here at midnight, and you start it to use at 7 o'clock in the evening. So you have 24 minus 19, then you have here 5 hours of use. And here, for example, your load, your light bulb, LED light bulb has 10 watts. And so we have 5 times 10 watt hours divided by, for example, 0.9. You go on with the next load, for example, a TV set, maybe it takes 100 watts and you watch TV for 2 hours, and so on. You have to just make a table with every kind of load and its consumption in terms of power and duration of use. The next step, you design the battery. So you take a look at the maximum depth of discharge. If you have here, I'll come to this, if you come to the battery chapter, usually you take as an optimum about 50% of maximum discharge. If you have a lithium-ion battery, then you are able to discharge significantly more. For example, here the recommendation is about having 90% of the discharge of the nominal capacity. And also, as I mentioned, the days of autonomy, so you have 4 to 5 days. Here's only mentioned 4 days. Some locations where it rains a lot, so maybe 5 days is better, and 2 days in the tropics. So that's the size of the battery. So this is energy capacity of the battery. So this is the energy of the load, what you calculated here. Then the days of autonomy divided to the maximum depth of discharge. Then the next step, you come to the energy that has to be generated by photovoltaic to supply the loads, and including the losses by the inverter, for example, and the battery. And you see here, so the energy to be generated by photovoltaic is the load divided by the conversion efficiency of the charge control and the battery. The inverter is already included in the load here, so we don't have to consider it once more. So the daily irradiance at a typical day, and while it has to usually work through the whole year, you have to consider the worst month of operation. Either do it by own measurements or other measurements, or by tables, or in some simulation programs you have that. And this is a good, it's not really a rule over thumb, but almost. You have just the daily irradiance and the worst month of operation. So this is here. And by this you are able to calculate the area of the PV generator. So you have here the PV is then the energy to be generated by a PV divided by that typical day at the worst month of operation, then times the performance ratio, then the efficiency under standard test conditions. Or if you can put this to those, this would be efficiency under actual operating conditions, but here it's separated performance ratio for the localization and the efficiency under standard test conditions. You can also calculate not only the area, but the nominal power of your PV generator. So this is here the P and the STC, or expressed in watt peaks. And you have here this area here times E, the irradiance under standard test conditions. I suppose everyone knows it, it's 1000 watt per square meter. And here again the efficiency under standard test conditions. So you see here it's on the lower part, and here's on the other part, so it gets eliminated. And so you can make this expression a bit easier. So you just have, if you calculate the power under standard test conditions, which is usually the way how you buy PV modules, you have just your consumption, no, not the consumption, but the energy we generated, times 1000 watt per square meter, times the relative irradiance during a day, also expressed in kilowatt hour per day per square meter, and times the performance ratio. We do this in the exercise, and so you a bit more. This is the market for autonomous systems. So you see here the other options, for example, by conventional batteries, here in almost blue color, or we call it turquoise color. Here you see, for example, if you have a wristwatch powered by a normal battery or pocket calculator. The battery itself is quite cheap, but if you really calculate the energy cost of such a battery, you see you have about 10 by a power of 4 kilowatt hours, so it's mean 10,000 euro per kilowatt hour costs such a battery, so extremely expensive. And here you have the costs for photovoltaic systems. That means photovoltaic generator plus BOS costs plus battery, and you are here much cheaper than that here. These are for two locations. The yellow part is for southerly locations with an irradiance value of about 1,800 kilowatt hours per square meter per year, while here the upper part is more relevant for Germany with yearly irradiance value of 1,000 kilowatt hours per square meter per year. So easily competitive with that. So you also many watches which have a solar cell already, or calculators which have a solar cell. So this is no questions. It's much cheaper than batteries. Also torch, or what you saw in the last years, that electrical kettle fans. If you go hiking in the mountains, you see just electrical kettle fans, and they get substituted by photovoltaics because it's much cheaper, as you see here. If you go further, you see gasoline generators, 1 kilowatt photovoltaic is always cheaper, even diesel generator to 10 kilowatt or diesel generator to 100 kilowatt photovoltaics is cheaper. Especially this is a bit older graph, but nowadays you are really below that values. But this depends on a lot of side parameters. How much is the local diesel cost? How much are the maintenance costs for the diesels? And how much good are the operating conditions, and so on. And here you see the grid costs for small consumer tariff. So photovoltaic here in this graph is still more expensive. But as you think that yesterday there was news that a tender in India, there was the autonomous PV, as a photovoltaic, including BOS and battery, has been assigned for $0.38 per kilowatt hour. So that includes photovoltaic costs plus battery costs, and this means that it has been really here very much in lower area, and is cheaper than many other. No, sorry, it was not 38 cent per kilowatt hour, 38 euro, $38 per megawatt hour, and this means 3.8 cents per. So it was here in this area here below that. So it was here in the very low area, and that's possible nowadays. It was a very big power plant. I think 400 megawatt was the size of it, and so it's even competitive now with grid tariff in many locations. Here you see the cost share of a small PV system, autonomous PV system, such as a solar home system. You see here the costs over 20 years. So not the modules are decisive cost options. The batteries are really most cost, the highest cost factor there. Also inverter. So usually not sure if you should talk about a solar PV system. It's just a more battery PV system. With photovoltaic gives the supply, the power, but the cost share is less than half cost of the battery. This is a quite good battery, even though it would last 10 years, and it is to be exchanged. So So this will be purchased in exchange after 10 years, and therefore the total cost is really high. If you have very cheap batteries, they are cheaper in the beginning, but on the long term they may last only 4 or 5 years. Some of them, if you use automatic batteries, they only last 1 or 2 years, and so you have to substitute them frequently. At the end, you end up more expensive than these costs here. Important points for photovoltaic implementation. So as I mentioned already, the irradiance is important on site. The land costs, security, grid connection costs, legislation for grid feeding. This is really important to take all these factors into consideration. The financing, so how much you get for your electricity, the power purchase agreement is called nowadays. Formerly, it very often premium tariffs have been applied. And what's also important is inflation compensation. This hasn't been the case in Germany, but many other countries, they offer inflation compensation. And in the future, it will be more important carbon trading. So if you substitute a conventional power plant by your PV power plant, you can have an extra benefit. This depends very much on the year and the country. So Germany starts next year with a price of 25 euro per avoided ton of carbon dioxide. In other countries it's much more. As I mentioned, in Switzerland it's about 80, and Sweden is 100 to 120 euro per ton of avoided carbon dioxide, and so on. Taxes, tax reduction, this is a special issue in the United States. So if you have a company and you spend your money on photovoltaics, you can get a significant tax reductions. Some countries, there are subsidies for photovoltaics. Interest rates plays an important role. If you pay a very high interest rates, it's sometimes impossible to finance PV power plant. And as I mentioned already, the inflation rate is important. The equipment, you have to have equipment that's suitable for high operation temperature, high sand and salt contents of air, the ultraviolet stability, the warranty. Though this is important that the warranty is not only valid in China, so you have to have a local dealer who would substitute, for example, your solar modules if they don't work anymore. If you have to deinstall your own and send it to China, the warranty may be not that helpful. And important to check the values given by the manufacturer. You have to have independent testing of the power, of the durability, and so on, to make sure really, because you have a large power plant, this is some considerable investment, and you have to make sure that the modules really achieve the required yield during a year and during lifetime. The infrastructure, so how is the importation if your country is not making own modules? What does it cost? How long does it take to the transport to the location on site? The mounting equipment is already there. How is the logistics there? The tools you need there, do you have to import them there? Are they available locally? Very important is the accessibility of the location of installation. If it's very far away, it may be difficult and very costly. Installation team, yes, sometimes it's cheaper than in Germany, usually not more expensive than that. But very important is the training of a local supervisor who is able to, who understands something of photovoltaics, and he's able to avoid problems and possible defects and so on. Related to that is the maintenance. So you have to keep the PV power plant running for 20, 25, 30 years, and you have to have some financing for that, continuous financing for that. Sometimes a supervisor, someone who is doing, who gets the material and does the substitution of defect components. Problem management also related to that, so someone has to see the problem and how to deal with that, are there spare parts or not, and so on. And also future development might be important. If you have a remote area and you supply electricity to that, it might be an important factor for many people to move there. and so your electricity consumption is drastically increasing, and maybe your power plant is not designed for that, and so you should think also about an extension of your PV power plant. Also, non-technical issues play a big role in PV implementation. So, for example, the cultures. So often short-term solutions are often preferred. Also for politicians, they want to have a quick success because they vote only for a short time period and they want to show off. And so if you have a PV power plant that gets profitable only after 10 years, they don't like it a lot. They want to see a quick profit and so on. Also by the politicians, there's also focus on prestigious, centralized, large-scale solution. Nuclear power plant is something where the politicians or even a whole country can show off. Photovoltaic power plants are not so suitable for that purpose. And also the deficits in education and competence in general and PV in particular. So the decision makers and stakeholders are not really aware that photovoltaic got really cheap. It has been in Middle America, so we got some offers there where photovoltaic was still calculated with $20 per installed watt. And nowadays you are below $1 per installed watt, including everything, modules, inverter, balance of system costs and installation. So there could be some misinterpretation in the related costs here. And the authorities, so it's important to let them know what the state of the art is and what the actual costs are. Legislation, while some ministries don't know how cheap PV is, they think the only option to supply a remote area is diesel, and so they give subsidy for diesel supply in remote areas in order to avoid that the local population is all coming to the cities. So it's good meant policy, but it's sometimes deadly for photovoltaics. You would have been profitable with photovoltaics and competitive with diesel, but not with the subsidies for diesel. If it would be a fair level playing field, then photovoltaic would be a problem. But if you have subsidies for diesel, then it's not feasible. Long-term financing, in many countries you have high interest rates, so you have to maybe find a financing from countries like in Europe where you have almost zero interest rates and get a financing from there, because if you go to Bangladesh or something like this, you have interest rates for photovoltaic systems which are in the vicinity of 30% per year. Also missing PV marketing and lobbying, because people are not aware of the opportunities, a bit afraid of installing new technology because they think could be risky. But if you can show them some good examples, then this will be overcome in some years and so on. And yes, PV costs are transparent. This is quite, you can even see it in satellite photos, that 1 square kilometer of photovoltaic is about, with efficiency of 16%, 160 megawatts, and this represents of 160 million euro, and the variation is plus minus 10% only. So this is quite transparent, but this is not so good for people which are subject to corruption. So they want to gain something extra and so on, and so they don't like this transparency here, and they prefer other options. For the large-scale power plants, if you deviate some money from that, it's hardly visible or transparent and so on. So this is also an issue. We come to the next part. Is now not off-grid systems, but grid-connected systems. I call it PV 2.0. And here you see A house which has been powered by photovoltaic system have been installed 1.5 million times in Germany during the last 2 decades. And you have the PV generator, the connection box, the DC connection box, and it goes to the inverter, and then you have here the meter kilowatt hour counter for both for consumption and PV injection. In Germany, these are 2 different tariffs, so you have to have 2 different meters. In some countries where you have a net metering, so you get the same amount of money for your grid injection then as you pay for your consumption from the grid. So you need only 1 meter, which does a balance between consumption and grid injection. Then you have for loads. That's really important in Germany now because you only get about 10 cents per kilowatt hour for your grid injection, but you pay for your consumption about 30 cents per kilowatt hour. And so it makes much sense to use directly your own generated electricity from your own PV generator, because you can produce it below 10 cents per kilowatt hour. Sure, it's not the right load here, light you need during nighttime, and photovoltaic only generates during daytime. So if you don't have a battery, we come to this solution a bit later, but without battery you should have loads here, for example charging your electrical vehicle, or your dishwasher, or your washing machine, or your refrigerator, and or your freezer, which you should supply by that load, directly by photovoltaics. So important is an effective feed-in legislation. So you should get some money for that, either by a power purchase agreement or by so-called premium tariff. So this is the typical grid-connected house. So this in Germany or many other countries. Here are some examples. This is a grid-connected house in Freiburg, in southern Germany. Even that particular house produces more than it needs, so it's even able to sell the electricity to neighbors, so it's called plus energy house. As another example, this is the airport in Munich, which features a 2.2 megawatt system on the roof. Here we have an 11 megawatt system in Serpa in Portugal. People even talk about photovoltaic landscape, because they got such big extension, so they use sometimes landscape architects in order to make it more pleasing. It's not the case here, but for other examples. It's a 67 megawatt power plant in Germany on an old Russian airport. Another also on an airport, 84 megawatts in Fino, north of Berlin. Here there's a 100 megawatt system in China. So it's really hard to take a picture of it. So it's a kind of panoramic picture, just all around the locations covered with photovoltaics and some wind power, as you see here. Here you see the grid injection, which is not anymore on the mid voltage level, but on the high voltage level at 110 kilovolts. Also with that, if you have a large scale PV systems, it doesn't make sense to do individual cleaning and maintenance, so you have automatic machines or even robots which do the maintenance and the cleaning of PV panels, as you see on these pictures. So we come to the exercise. This is a design of an off-grid solar home system, including an inverter. It's located in a tropical location in Rio de Janeiro, Brazil, and we have a typical irradiance during the first month of the year, and that is there about 4 kilowatt hours per square meter per day. Comparison, if you would have applied that for Germany, some locations is 1 kilowatt hour per square meter per day, some locations are even only 0.5 kilowatt hours per square meter per day. And in that location we have the following energy needs. We have a ventilator starting at 9:30 in the morning when it gets hot, and it runs until 1 hour before midnight, 11 p.m. Then we have conventional light bulbs still at 60 watts. that are operating from 7 p.m. until 11 p.m. We consider the next page to see some energy saving options. Then we have a notebook computer that operates from 6 p.m. to 9 p.m. that has a consumption of 30 watts. We have a TV set of 100 watt of consumption that operates from 8 p.m. to 10:30 p.m. And the tasks are, you should calculate the load, respectively the daily consumption that should be supplied. Then you should calculate the battery size for 24 volt battery. The battery cycle efficiency or round trip efficiency is 80%. We have to consider the efficiency of the charge controller, which is 95%, and the inverter efficiency is 90%, so considering all the different load conditions. We have the panel size we have to calculate. We consider a PV panel which has a nominal efficiency under standard test conditions of 16% and a performance ratio of 0.8. That's typical for tropical locations because it's rather hot, and performance ratio is a bit less, for example, than in Germany, while it's colder there. We have to calculate the costs. The initial costs and the specific costs of the small KE during 20 years for a yearly irradiance of 1,800 kilowatt hours per square meter per year. We have the following site conditions. We have a PV panel that costs, including duties, about €1 per watt peak. Lifetime is 25 years. And a battery of €300 per kilowatt hour that has a lifetime of 4 years, and a mounting and support structure of €0.50 per watt peak that has a lifetime of 25 years. As mentioned before, we have to consider first, in order not to calculate that load, we just should think about how to lower that load. And in the case for the light bulbs, it's quite easy. We can substitute those 60 watt light bulbs by LED lights which only consume 8 watt each instead of 60 watts. So the original consumption 5 times 60 watts times 4 hours would have been 1,200 watt hours, while we have the consumption of the LEDs, we only have 8 watts times 5 pieces times 4 hours, which 160 watt hours only. So we have 86.6% of energy saving. So consider this first, and then do the tasks what have been given there, and I give you a solution then. Thank you very much.